All right, picking up where we left off, in addition to varying the size or length and branching and double bonds, where they're located, whether we can form circular things, all of those variations, there is one added thing to these complex carbon molecules, and that's the idea of isomers. Okay? And we've actually encountered this before, but we may not have really focused in on it. So isomers are compounds that have the same molecular formula, but their structures are different, and consequently their properties are different. Remember, structure is function. So there are several different types of isomers. One is structural isomers. That's where you have different covalent arrangements of their atoms. Okay, and I'll give you examples of all these here in a moment. Let me just kind of list the different versions. Another version is something that we call cis-trans isomers. This has the same covalent bond arrangement, but spatially its arrangement is slightly different. Okay. Third is enantiomers. These isomers are actually mirror images of each other, and that can have a very profound consequence. All right, so let's give you examples of these so you can kind of visualize. So with structural isomers, here's an example. Here's pentane, so it has 5 carbons, 1, 2, 3, 4, 5, and it has 1, 2, 3, 4, 5, 6, so 12. 12 hydrogens. Over here, we have the same number of atoms of each, but they're arranged differently. So 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have the same formula, but it looks very different. Okay, so these are structural isomers. Cis-trans is all dependent on double bonds. Okay? So remember, when we have a double bond, that we have a planar structure. Consequently, when we have this arrangement here, where both of these x's are on the same side, that is very different than when we have this trans conformation, where the x is on the opposite side, or trans to this double bond. So this is on the same side of the double bond. These are on opposite sides of the double bond. Okay. Now, if you recall, I talked about the idea of liquid oils, such as olive oil or vegetable oil, being a liquid instead of a solid because it has these double bonds which forms kinks. Okay, so if you can imagine a long hydrocarbon chain that comes up to here, and then a long hydrocarbon chain extending off of here, this would produce a kink in that chain. Okay. We also can have fats that have this trans arrangement, but they are not found in nature. And when you do introduce them into at least the human body, this can lead to or contribute to heart disease, because our body isn't expecting to or know how to handle this type of an arrangement. Okay, so if you ever heard of trans fats, that's what they're referring to here. All right, the last category here is when you have the same types of groups attached to the central carbon. So here we have a carbon, and we have an NH2 group over here. Over on this side, we have a carbon, NH2 group over here. Up here, we have a CO2H. This is something that we call carboxylic acid. Here's a methyl group. If you look at the arrangement here, this group, the carboxylic acid group, is on top. Okay, that's true for that. But over here, the NH2 group is on the right side. Here it's on the left side. Now let's look at that in comparison to the methyl group. The methyl group comes out towards us. The hydrogen goes behind. Again, methyl comes out towards us. Hydrogen goes behind. So you can see that these are mirror structures of each other, but this is important because imagine if this structure was sitting down on a surface. If it's sitting on a surface, it's probably because it has binding interacting with these different groups. If you have this structure that can bind to another molecule, this mirror image would not be able to fit in the same slot because these three points are on different arrangements, so they're mirror images. So you could, if you tried to put this over in this slot, you could engage two of the three sites that are sitting down on the bottom, but you couldn't engage the third one. Okay? This has a very real consequence, particularly in the pharmaceutical field. So oftentimes, when you have a drug, there are two versions of it, two isomers, and those two isomers can have very different effects, or one can have a much stronger effect over the other, or they could even have opposite effects. Okay? So let's take a few examples here. So here's ibuprofen. We are probably familiar with this in that it reduces inflammation and relieves pain. Here is the most active form of it. It is the S form. The mirror image of that is the R form, and it is 100-fold less effective than this. So you'd have to take 100 times more of the R to get the same or similar effects that you get with the S. Okay. Another thing we have here is albuterol. If you have asthma, you are probably very familiar with this. This is what you have in those little puff inhalers, right? What it does is it relaxes bronchial airway muscles and allows you to breathe easier. The active form in here is this, okay, the R form. The mirror image of it, the S form, actually has the opposite effect, right? So it would actually make the asthma worse. Consequently, when we make albuterol, we have to make and purify only the R form. In ibuprofen, both the S and R form have similar activities, it's just less strong. So the fact that the R is present is not that big of a deal, so we just give you the crude combination of the two and just make sure you have enough of this S form. So, concept 4.2, carbon atoms can form diverse molecules by binding to 4 other atoms. We talked about how this arrangement is in a tetrahedral structure. If you have 2 carbons, you have 2 tetrahedral structures. They would slightly rotate around that carbon-carbon bond to not interfere with each other. But if we change that to a double bond, it now becomes planar, right? And this is what leads to that cis-trans issue. We discussed how we can change these carbons by length of the carbon chain or whether there's branching, where the location of the double bond is, or if we can form a ring. Okay. We discussed how these combinations of carbon and hydrogen are called hydrocarbons. They are both nonpolar, consequently hydrophobic. They are also a good source of energy. We discussed how there are different isomer versions here. So here's structural isomers, cis-trans, again, looking back at the planar structure of this double bond. And then finally, enantiomers, which are mirror images of each other. And we discussed how this is important because sometimes that can impact whether a drug is effective or not effective, or actually harmful.